So this is a quick summary of motion of an object, and for us, O-level A math restricts the motion to just motion in a straight line. Okay, and there are three parameters that we are interested in. We are interested in the displacement of this object, the velocity of the object, as well as the acceleration of the object. So if we have information about all these three things, we will have quite a complete picture of the motion of the particle or object in that straight line. Okay, so one of the important things to note is how these three quantities are related. You had a hint of this even in EMATH, because when you have distance time graph, we always said that the gradient was the speed, or gave you the speed. So gradient in this case for displacement time graph will give you the velocity. All right, so velocity is described as the rate of change of displacement. And if you have a velocity time graph, the gradient tells us the acceleration. So acceleration is dv dt. Okay. So this is the part that has to do with differentiation. But we can also look at reversing these operations. Okay, so if you have displacement differentiated with respect to time giving you velocity, velocity differentiated with respect to time giving you acceleration, we can reverse it. So if we integrate acceleration with respect to time, we will get velocity. And if we integrate velocity with respect to time, we will get displacement. Okay, so this is the part that we'll be going through today. Now, the other part I'd like to talk about is what we started off when we were looking at motion of an object in a straight line. So two things we must specify. We must indicate what is the reference point. Usually we are told it is a fixed point. Sometimes we call it the origin. And there is some idea of a positive direction. So usually the motion or the direction you're moving at the beginning is taken to be the positive direction, and we take reference from there. Okay, so for example, if I have a particle, so let's say the particle is moving from this origin and it goes somewhere to the right, slows down and stops, and then it moves backwards this way. What can we say? Okay, so first of all, we can talk about the displacement. So from here to there, the first leg of its motion, we can say that the displacement is positive. All right, it comes to a stop and then it starts moving backwards. Now, in the second leg of its motion, the first part is actually still positive displacement until it returns back to the origin. And if it goes past the origin, then we will start saying that the displacement is negative. Okay, so if you like, it is as if this has a ruler, and this ruler is marked this way, right? +1, +2, +3, +4. And then if you are on the left side of origin, then it is -1, -2, and so on. Okay, so our displacement tells us location, and there is such a thing as a positive as well as a negative displacement. Okay, still on the particle, and it is moving from here, slowing down, and then comes to rest momentarily, and then it turns around. All right. Now, the motion is a straight line, but I draw it like this so that you can see that there is actually a forward motion and then a backwards motion. So in the first leg of the motion, which is from here to there, what we can say about the velocity is that the velocity is positive. And the reason that the velocity is positive is because the object throughout this part of the motion is moving to the right or heading to the right. The backwards motion throughout this part, we will say the velocity is negative. All right. So an example of how we might illustrate this, at some point over here, we might say this is the arrow indicating the velocity. Whereas at some other point on its way back, okay, we will draw the arrow the other way around. And since the arrow is pointing to the left in the negative direction, velocity will be treated as negative. Okay. Now, one question you may be wondering is this: the particle started from the origin. How did it suddenly move, and then why is it slowing down? Okay. So one possibility could be imagined. You can imagine that one possibility is the particle is attached to an elastic string. Elastic string. Okay. Initially, let's say it is not stretched. Okay, so the string is here and the particle will stay there. The string is attached to the wall. Okay. So this might be a possible context. Now, what causes the particle to move is possibly you hit it. Okay, so you apply a force, hit the particle to the right, maybe using a hockey stick, and then what happens is the particle will start moving to the right. But because the string gets more and more stretched, the particle will start slowing down until it comes to rest at some point. And then because the string is still stretched, it will pull the particle backwards, and then the particle starts accelerating in the other direction. Okay. Now, what the acceleration is then in this case is the acceleration is throughout the whole motion pointing to the left. So even though the particle started off with a certain speed, it continues to slow down. It continues to experience what we call deceleration or negative acceleration. All right. Okay, so I'm in a sense doing a little bit of introduction here to prepare us for the questions that we're going to be looking at. So let's talk about the difference between indefinite and definite integral. Okay, so we'll give two examples. Okay, so to do that, let's say we start off with looking at differentiation first. Okay, we have y equals to x squared. And if you want to find the gradient at different points on this graph, we differentiate with respect to x, and what you get is 2x. Okay. What if we have another graph that is y equals to x squared minus 3. What happens when you want to know the gradient at different points on the graph? You differentiate this, and oh, it actually gives you the same derivative 2x. You will see the same thing happening if you choose something above this. So if you have y equals to x squared plus 4 and you differentiate it, you will also get 2x. What this means is if you now perform the reverse operation and integrate 2x, you integrate 2x with respect to x, we get an indefinite integral. Okay, it is called an indefinite integral because we are not really sure which of those original graphs this thing came from. So we have this arbitrary constant c. In other words, every time you do an indefinite integral, you must include an arbitrary constant c. We can determine what this constant c is if certain information or pieces of information is given. So if a specific piece of information is given, if we are given a specific piece of info, it can help us find this arbitrary constant c. Okay, so what kind of info are we talking about? Maybe we are told that when x equals to 0, y equals to 0, meaning to say the original curve is that specific one, the only one that passes through the origin. Okay, so when you apply it, then you will have y equals to x squared. So y equals to this, right? Okay, so y equals to x squared plus c would then imply 0 equals to 0 squared plus c, and then c equals to 0. So we have a specific graph in mind, which is y equals to x squared. Okay, so without that specific piece of info, what we are doing here is what we call an indefinite integral. Okay. Okay, what does a definite integral look like? A definite integral has lower and upper limits. So you could be integrating 2x dx, let's say x going from 1 to 3. Okay, going from 1 to 3. So we saw this in one of the worksheets. So the way we do this is we integrate, it gives us x squared, and then we integrate on the outside of the square brackets the lower and upper limits for x. What we do next is we substitute these values of x. So when x is equal to 3, you have this. When x equals to 1, you have this. You subtract 1 from the other, and your answer is 8, which is the definite value of the definite integral. Okay. Now, you may be wondering what happened to the arbitrary constant. So I'm going to do the same integration. You will see that the arbitrary constant actually is unnecessary because when x is equal to 3, x squared plus c is 3 squared plus c. And when x is equal to 1, x squared plus c is 1 squared plus c. So the arbitrary constant always cancels itself off, which means actually this plus c is actually not necessary to write down. because it will always cancel off. Okay. All right. So this is the introduction. Let's now head back to where we stopped in the last lesson. So here, displacement of the object is given by this expression, and displacement is in terms of t. So question is asking, first part, show that the displacement is positive during specific time intervals. All right. So I have done the first part. If displacement is positive, you bring in the inequality. All right, and then what you have actually is a cubic expression. I put there in brackets that 2t is always positive. So if 2t is always positive, in a sense, you can divide both sides of the inequality by this positive expression. And the inequality will still be true. Okay, so another way to look at it is to say, you want this whole thing to be positive, but this first chunk is already positive. So what does that mean? That means that this second chunk here must be positive. Okay, so that's another way to look at it. So this first one is positive. The second part must be positive for the whole thing to be positive. Okay, when you reach this last bit, there is something that you need to be always doing. So can I describe this for you? I will describe this as a quadratic inequality. So every time you encounter a quadratic inequality, please do this, sketch the graph. Or can I say it this way? The best way to solve an inequality involving a quadratic is to sketch the graph. Okay. So actually, when you sketch the graph, you are comparing two graphs. Okay. Can I check? Have I drawn my quadratic curve correctly? Answer is yes, right? Why? Because the coefficient of t squared is +1. So my quadratic curve is upright and it cuts at those 2 points. Okay. So when you solve this quadratic curve, actually what you are saying is when is y equals to left-hand side, greater than means above, y equals to right-hand side. So when is your quadratic curve above the horizontal axis? So if you're an ant walking from left to right along this axis, guess what? Throughout this part, you have to keep looking up at the quadratic curve. And throughout this part, you have to keep looking up at the quadratic curve. Okay, so the periods of time when you look at the quadratic curve is when t is less than 5 or when t is greater than 7. Okay, but because t here represents time, you need to also indicate that it does not make sense for t to be negative. So there is another restriction over there to specify t must be greater than 0. Okay, so we have got the displacement. How do we, from the displacement, get the velocity? So remember, velocity is given by the derivative of the displacement. So what we need to do is to differentiate s. And what is s? not so good to leave it in this form, right? Which is 3 factors. So why don't we multiply them all together? So let's expand this thing. So it's 2t times, I think it's 35 minus 12t plus t squared. Okay, to minimize confusion, let's use square brackets. Okay, I've not done the differentiation yet. Okay, let's expand some more. So you have 70t 4t squared 2t cubed. Now that it's expanded, very easy. I just differentiate term by term. 70 minus 24, differentiate 2t squared is 2t plus 2, differentiate t cubed is 3t squared. Okay, so the expression for velocity is this, which is a quadratic in t. Okay, determine the values of t when the particle comes to instantaneous rest. So when it comes to instantaneous rest, we are talking about velocity equals to 0. So if you set v equals to 0, you are looking at this. Let's simplify this a little. Yep, and then you find the two values of t. So t equals to minus b plus minus square root b squared minus 4ac over 2a. Okay, and then you get your answers. Okay, obtain an expression for the acceleration of the particle. So how is particle's acceleration related to velocity? You differentiate the velocity. So we are talking about differentiating with respect to x, this expression, right? And you get minus 48 plus 12t. And the next part, last part, is linked to this. So when the particle is decelerating, when the a is less than 0. So if this is less than 0, you will get this, you will get this. And of course, because t is again time, t has to be greater than 0. So what we saw in this question was being able to move from displacement to velocity by differentiating, and then from velocity to acceleration once again by differentiating. In the next worksheet, we need to be able and flexible enough to be doing backwards and integrating, but that's a fairly straightforward and simple task. Let's start off with something we are familiar with. So in the first question, this looks very much like an EMAF question, right? Under the topic of graphs of functions. There are 3 distinct parts to the motion of this particle in a straight line, and this is a velocity time graph. So the slight difference in this case is that typically we are not focusing so much on how v is related to t, right, for EMAF, but here the equations are given for the 3 time intervals. Originally, when I set this question, I thought to ask you to derive lah. So, if the velocities have not been given, by right, you should still be able to derive each of the three functions. Okay, so you're expected to know how to derive this, derive this, derive this for the three from the given. Okay, the middle one is obvious because v is equal to 3 and stays constant throughout the time interval. Okay, for the first and the last, you need to actually first determine the gradient and then use y equals mx plus c with one of the coordinates. Yep. For this other one, maybe instead of y equals mx plus c, a better version of the equation to use, I shouldn't talk about y here. I should be saying v minus v1 equals to gradient t minus t1. Okay. So what is the gradient? Need to use the appropriate formula, and you should get a negative answer for m. All right. If you look at the answer we have there, the gradient is a negative 3/4. Two things we are always talking about when we look at the velocity time graph. So this is again repeating EMF work. If you have velocity time graph, the gradient tells you the acceleration. The area under the graph tells you the distance covered. Okay, so at this point, I'll just make a brief comment. Area under the graph tells you the distance traveled. But distance traveled is not the same as displacement. So just be aware of that. Okay. First part, find acceleration at different points in time. So that's a pretty straightforward thing, right? So for part A is equal to dv dt, where v is 3t, and the answer is 3. So what does this mean? In the first leg of the motion, acceleration is 3 meters per second square, and it stays constant. How about in the middle portion of the motion? Acceleration is d dt of v, which is a constant 3. And differentiating a constant gives you 0. And it tallies with what we know. The speed does not change. There is no acceleration. Finally, A here is d dt of this linear expression. Differentiating the first term, you get this. Differentiating the second term, which is constant, you get 0. And this again tallies with what we said earlier on, right? The gradient, which is minus 3/4, is the acceleration. Okay, so for the next part, it's a little bit more trickier, so you got to be aware of it because we are now going to do integration. And what you need to be aware of is when we are doing integration, we are doing an indefinite integral. Do not forget to put the arbitrary constant. Okay, so for the first part of the motion, what we have is v is equal to 3t, right? So the displacement s, let's call it s, is equal to the integral of velocity. And we are integrating 3t with respect to t. You will get 3/2t squared. And if you took note of what I just mentioned, this is not the correct and complete answer. What needs to be added is the arbitrary constant plus, shall I just say C1. Okay, so I need to see, is there something that I'm given that can help me find C1? Yeah, because if you look at the what we are told in this case, okay, it starts off from the fixed point O and it starts from rest. So we know since it starts from the fixed point O, we can say given that when t goes to 0, s equals to 0. So s equals to 3 over 2 t square plus c1 uh, 0. So from t equals to 0 to t equals to 1, the formula for s is 3 over 2 t squared plus 0. So that answers part A. Okay, in the meantime, as you're trying, I'm going to sketch the graph, displacement time graph, so that it will help us. Okay, so we've got an equation. You should be getting this. I call this new arbitrary constant C2. What information should I be using to apply to this? Okay, so incorrect. What is incorrect? Let me put it here. Incorrect to say when t equals to 0, s equals to 0. Why is this incorrect? Since we are now talking about motion from t equals to 1 to t equals to 6. Okay. So this is where the graph that I drew, the first part for displacement time graph may come in helpful. I drew an incomplete graph. What is that missing dotted value over there? So this is where I will use part A's answer. From part A, when t equals to 1, s equals to 3 over 2 1 square, which is 3 over 2. And this set of values applies to the next part of the motion. So now I can substitute to this s, which is 3 over 2, equals to 3, 1 plus c2, and I have c2 is equal to minus 3 over 2. So from t equals to 1 to t equals to 6, this new formula is s equals to 3t plus c2, which is minus 3 over 2. Okay, let's try to connect. So I have this one from part 1. So let's put it here from A. I got this value from A. And I used it to help me find part B. How do I draw part B, which is duration from 1 to 6? Okay, finally for part C, how do I find the displacement, integrate velocity? And the displacement was given as minus 3 over 4t. what is it? Plus 15 over 2. So when you integrate this, you will get minus 3 over 8 t squared plus 15 over 2t, and I'm highlighting it, plus C3, the new arbitrary constant. But in order to find this arbitrary constant, actually I need the help of my answer from part 2, right? So what I need to know from part 2 is this point at t equals to 6, what is the s value? Okay, so I go back to part B. What happens when t equals to 6 for part B? Then s is equal to 1833 over 2. Okay, so I'm going to use this for use these values for this new equation. So the new s is 33 over 2 equals to this one, t6 plus c3. Okay, and then you work out what is c3 over here. Negative 15 is what I get. So from t equals to 6 to t equals to 10, this is the expression for the displacement, minus 3 over 8t squared plus 15 over 2t minus 15. So what the question here says is the particle is initially at rest at a fixed point O. How can I phrase this or use this information and form some statements mathematically? Well, I can say initially means when t is 0. Where's the particle? At 0 displacement, your fixed point O. What was its velocity? It was initially at rest, velocity is 0. Okay, so this is a helpful way of making sense of the first statement. So what we are given in this case is acceleration in terms of t. So state the time interval during which the particle is decelerating. So decelerating means a is less than 0. Answer t less than 4, but because here t is time, we will say this is the answer. So the time interval is in the first 4 seconds. Velocity from integrating acceleration with respect to time. So when you integrate this, although in the end this is the final answer, we need to see an arbitrary constant. How to find this arbitrary constant? Use information provided. And the one that's going to help us, when t goes to 0, velocity was 0. So 0 equals to, substitute t goes to 0, and you get, okay, c goes to 0. So what does that mean? I can now give a definite answer what the velocity is. I no longer need to write it in terms of an arbitrary unknown constant to factorize it. So what are the things I'm looking out for, or we can look out for? So you have here coefficient of t square is positive, right? So your quadratic curve is upright and it's cutting the horizontal axis at 2 points, t equals to 0, t equals to 8. Those are your horizontal intercepts. But there's nothing happening for negative t. So in the end, the graph will look like this. And we stop, or the question tells us to stop at t equals to 12. This should be t equals to 8. To complete our sketch, we need to get some of the critical values. And the question also wants us to clearly indicate what is the maximum speed of the particle and when does it come to instantaneous rest. Okay, so what is this value over here? And would this be the maximum speed of the object? So what we need to do is substitute t equals to 12 to get the v. The v will be 12, 4, which is 144. Okay, so the speed here is 144 meters per second, which is incredibly fast. But I need to also actually double check with this one, right? Although it is a minimum turning point, if this value were, let's say, minus 200, then even though the velocity is minus 200, it actually means that the speed is 200, and that should then be the maximum because it's even bigger than 144. So what is this? All right. Now, can I say that this value here for t is equal to 4? And the answer is yes, and the reason is because it's quadratic. All right. I can do this and only because I'm looking at a quadratic curve. So a quadratic curve has a line of symmetry. T equals to 4 is the line of symmetry. Let's do another calculation. When t equals to 4, velocity is minus 48. Nowhere near 144. So I'm ready to make my concluding statement here. So I will say here, okay, indicating clearly. So A, maximum speed is 144 meters per second. Okay, when does it come to instantaneous rest? By that we mean when does the velocity equal to 0? We are not talking about the initial. So the first time it comes to rest is over here. So this is for part B. It happens at, so instantaneous rest at t equals to 8 seconds. How would we describe this motion? The graph is going to help us, right? So we see that for the first 8 seconds, velocity is negative. And then for the remaining 4 seconds, velocity is positive. If you think of the particle as moving along a straight line, so before we talk about the description, let's try to draw to make sense of this. What does it look like? So you have a straight line. There is an origin, fixed point, the particle started from rest here, right? And for the first 8 seconds, it was moving in the negative direction. So it moved. How long did it move for? Backwards for 8 seconds. So at t equals to 8, it comes to rest. And then what does it do? It turns around and then continues moving, right, at positive velocity. The particle moves in the negative direction. That's the first part. Comes to instantaneous rest. Okay, my spelling is wrong. Instantaneous rest at t equals to 8 seconds. And then moves in the positive direction. So displacement is the integral of velocity. Integrating this, t cubed 12t squared plus d. Okay, I choose a different symbol for this arbitrary constant. Well, we were told that the particle was initially at the reference point, the origin, right? So when t0 is equal to 0, so it actually means this. D equals to 0. This is our complete description of displacement. Let's look at the description of the motion. So this brown thing I drew here, it starts from 0 here, right? And then it moves negative direction until it hits, it comes briefly to rest at t equals to 8. Could this be the furthest it is from O? Question mark. All right. And then it starts to turn around. But I drew it in a way where I wasn't really sure how far it went. Where did it stop? Or where did it reach? Which point was it at when t equals to 12? We are interested only in 12 seconds. So actually the answer to that question is you just need to test 2 points. You test at the final t equals to 12. You also compare it with t equals to 8. So right now, I can't tell what the answer is. Okay, so we do not know. We will have to figure it out. So when t equals to 8, what is happening is the particle is momentarily at rest. It has reached the furthest it could go to the left of the origin. What is that furthest it could go? We are expecting a negative answer, by the way. So this is what we are expecting. Okay, so what is this value? Negative 256 meters. Now let's compare it with what happens when t equals to 12. Let's see which is bigger, and then we will make a conclusion. Okay, is the answer 0? The answer is 0. Maximum displacement is 256 meters from O in the negative direction. Okay, 2 points of intersection, t equals to 0 and t equals to 2. And because this is a quadratic curve, that's the shape, but we only want up to t less than or equal to 4. Okay, brief description of the motion. So, particle moving in a straight line, and for the first 2 seconds, it's actually moving in the negative direction. Okay, then it comes to rest at t equals to 2, and then from then onwards, it turns around. We don't know for how much or how far, all right? But the description will be similar to before. So particle moves in negative direction for first 2 seconds, comes to instantaneous. Okay, let me spell it correctly this time. Rest at t equals to 2 and can then move in the positive direction subsequently. Please note that even though your arbitrary constants are 0, the working is required, right? So the same thing happens here when t is 0, v is 0. Not v is 0. We need to say s is 0 in this case. So displacement is equal to this. What is the maximum displacement? So you can look at two specific points, right? When the velocity is zero, meaning to say S is maximum when ds dt, which is v, equals to 0. And velocity is 0 when t equals to 2. Okay, so go back to the graph. There you go. Velocity is 0 when t equals to 2. It is also 0 when t is 0, but that's not a meaningful point to look at. So let's check when t equals to 2, what do we have? When t equals to 2, hopefully we are looking at maximum displacement. So you have but let's check what happens at t equals to 4, right? Whoa, okay, 32 meters. So although you have a turning point here, we are going to say therefore the maximum displacement is at 32 meters from O in the positive direction. So although minimum maximum often has to do with turning points, sometimes I need to look at the shape of the graph. Okay, let me explain what I mean, and then we will stop here, right? So it's got to do with a graph that is like this. Let's say you have this. Okay, so if we are looking at a quadratic curve, you have this various values. Then what do we know is the minimum value of y? It is -4, and it happens at the turning point, and it is tied to the turning point, so it's tied to dy dx equals to 0. But when we are talking about y max, the value is 10. What is it tied to? It is tied to the extreme value of x. Okay, so we can tell only if we look at the graph. So I hope that makes things clear. So I just put here that this is just a note.